Yeah, good evening. So till now in the series of these lectures, we have just finished mole concept and stoichiometry, and I hope you have done enough practice for this chapter also. The next chapter is going to be, chemical bonding. This chapter is basis of complete chemistry, including organic and inorganic chemistry. So in this chapter, we'll revise the concept of, type of bonding, theories related to chemical bond, including valence bond theory, molecular orbital theory, and we'll do some introductory part of, this is related to hydrogen bonding, van der Waals force, Fazan's rule, which tell you about covalent character in ionic bond. We'll see detail of ionic bond, lattice energy, concept of dipole moment, and we'll see different theories and the limitation of these theories. So we'll find another term of resonance also. So in today's lecture, I will just try to summarize what is the meaning of valence bond theory and how bond is formed from, with the help of, let's say, valence bond theory, what is the meaning of overlapping of orbitals and all these things. So to start with the chapter, I will just try to start from the basic scratch basically. So we'll start from, revision from 9th and 10th class also. So including the definition of electrostatic bond, covalent bond, and slowly we'll cover up complete chapter. So as per, let's say, chemical bond is concerned, chemical bonding, it is most important chapter of your, any competitive exam preparation. So chemical bonding. Here we are going to discuss three different theories related to chemical bond. First is, this may be, let's say, Lewis Octet theory. Second is, valence bond theory. As per valence bond theory is concerned, it is VVT. And third one is molecular orbital. Molecular orbital theory, you can say it is MOT. So one is Lewis Octet theory, another is valence bond theory, VVT, and another is, let's say, molecular orbital theory, you can say it is MOT. We'll start from Lewis Octet theory, then we'll see quickly to valence bond theory, and then, it is molecular orbital theory, MOT. So according to, Lewis Octet theory, according to Octet theory, two elements combine to form chemical bond to, complete their octet or duplet. According to Octet theory, I hope you learned this theory in somewhere junior classes of 9th and 10th class. So according to Octet theory, two elements combine to form, chemical bond to complete their octet or duplet. And following bond formation can be explained. Following bond formation can be explained with the help of, Octet theory. with the help of octet theory. Let's say the first bond is it is going to be ionic bond. This bond is also known as, we know, electrovalent bond. As per ionic or electrovalent bond is concerned, we'll see here all detail related to ionic bond in a single shot. So as per ionic bond or electrovalent bond is concerned, the bond is formed, the bond is formed due to transfer of electron. For example, if it is Na, its electronic configuration is 2, 8, 1, and it will convert into Na plus while losing electron, and it is 2, 8. Same as per chlorine is concerned, it is 2, 8, 7, and it will gain electron, will convert into chloride ion, and is 2, 8, 8 as per electronic configuration is concerned. Once we have formation of, let's say, Na plus as a cation, and simultaneously, let's say, Cl minus as a anion. Once we have formation of, let's say, Na plus as a cation, Cl minus as a anion, the electrostatic force of attraction between oppositely charged or ion. So this electrostatic force of attraction between oppositely charged ion is known as, let's say, ionic bond. So I'm repeating again, as per ionic bond is concerned, the bond is formed due to complete transfer of electron. Here sodium is converting to sodium plus while losing electron, and chlorine will gain electron, it will convert into chloride ion. Once we have formation of, let's say, Na plus, and we have formation of, let's say, Cl minus, the electrostatic force of attraction between oppositely charged ion, which is Na plus and Cl minus, is known as ionic bond. As per strength of ionic bond is concerned, it is measured according to lattice energy, as lattice energy. So if we see as per lattice energy definition is concerned, lattice energy, so it is measure of strength of ionic bond. It is measure of strength of ionic bond, and it is energy released. It is measure of strength of ionic bond. It is energy released during formation of 1 mole of ionic lattice. It is energy released during formation of 1 mole of ionic lattice from its constitution, from its ions, let's say. It is energy released during formation of 1 mole of ionic lattice from its ion. For example, if it is, Na plus gaseous, when combined with Cl minus gaseous, can convert into NaCl solid. And for example, if X kilocalorie per mole heat is released here, then corresponding lattice energy. Correspondingly, you can say lattice energy should be equal to minus x kilocalorie per mole. So again, negative sign signify it is always the energy released. So lattice energy should be equal to minus x kilocalorie per mole. So I'm repeating again, as per ionic bond or electrovalent bond is concerned, this bond is formed due to complete transfer of electron. Now, due to complete transfer of electron, we have formation of ions and mutual force of attraction between oppositely charged ion is nothing but lattice energy. Yeah, it is ionic bond and corresponding energy released is known as lattice energy. Further, if you see the magnitude of lattice energy, magnitude of lattice energy is directly proportional to q plus q minus divided by r plus r minus. Magnitude of lattice energy is directly proportional to q plus q minus and whole divided by r plus r minus. For example, order of lattice energy order of lattice energy, it is, let's say, MgO. Suppose another compound may be, let's say, magnesium carbonate, and another compound may be, let's say, magnesium sulfate. Here the charge of magnesium oxide is +2 -2, magnesium carbonate is also +2 -2, and magnesium sulfate is also +2 and -2. So as per order of lattice energy is concerned, MgO will be more than magnesium carbonate and magnesium carbonate will be more than that of magnesium sulfate, let's say. Again, let's say they have same charge, but as size of oxide ion is much less than that of carbonate ion and size of carbonate ion is less than that of sulfate ion. So overall lattice energy, overall magnitude of lattice energy of MgO will be more than magnesium carbonate and magnesium carbonate has more than that of magnesium sulfate. Same if we have to compare the lattice energy of, let's say, lithium fluoride, it may be, let's say, sodium fluoride. Same, let's say this may be potassium fluoride, it is rubidium fluoride. So as the size of cation increases here, again the magnitude of lattice energy decreases. So magnitude of lattice energy is found to be proportional to mode of multiplication of charge divided by distance between both charges. And order of lattice energy, MgO, more than magnesium carbonate, more than magnesium sulfate. Further, lithium fluoride has more lattice energy than sodium fluoride. Sodium fluoride has more lattice energy than potassium fluoride, more than that of rubidium fluoride. So in general, you can say as lattice energy increases, melting point as well as boiling point of ionic compound increases. So it tell about how stronger we have, let's say, this ionic bond. Now further, as per ionic bond is concerned, you can say no ionic bond is 100% ionic as it acquired covalent character due to polarization. No ionic bond is 100% ionic as it acquire covalent character due to polarization of anion. We'll see the meaning of polarization of anion. So no ionic bond is 100% ionic as it acquired covalent character due to polarization of anion. No, sometimes it is also related to Fazan's rule, F-A-J-A-N. So it is something related to Fazan's rule in different books. For example, if you see the structure of NaCl, for example, if you see the structure of NaCl, so in the case of NaCl, here it may be Na plus, and you can simply imagine, let's say this may be, let's say, chloride ion. It is perfectly ionic compound. Now, somehow if we have, let's say, Na, and you can imagine this may be Cl, this will be the example of, here you can say this will be the example of covalent bond, as we have sharing of electron cloud here. So this may be, let's say, ionic bond and covalent bond. The actual situation may be something, let's say, in between. Here it may be, let's say, Na plus, and Cl minus can be, partially distorted. And here this may be Cl minus. So this bond is the example of perfectly ionic bond. It is ionic bond. It is the example of, covalent bond. And as per, let's say, Na plus and Cl minus is concerned, it is assuming, it is 100% ionic, hypothetically, and this is the actual situation. So no bond remain 100% ionic due to polarization of anion. And due to polarization, every ionic bond acquires certain covalent character. Due to covalent character, it affects the properties of ionic compounds also. So first we will measure how polarization, how much polarization can take place. So to understand the extent of polarization, you can define two terms. One is polarization of cation. Polarization of cation is, it is ability of cation to, it is ability of cation to polarize electron cloud of anion. It is ability of cation to polarize electron cloud of anion. And polarization power of cation. And polarization power of cation is directly proportional to, its charge divided by size. It is ability of cation to polarize electron cloud of anion. Polarization power of cation is directly proportional to charge divided by size of cation. Polarization power of cation is directly proportional to, you can simply say, charge divided by size of cation. So higher will be the positive charge of the cation, higher will be the polarization power. And if size is smaller, so polarization power of cation is again higher. Apart from, let's say, polarization power, if you see the order of polarization power, or you can say in general, in general, cation of D and F block element has more polarization power. Has more polarization power than corresponding S and P block element. So if you see in detail, the reason about is due to poor shielding effect of D and F orbital, their cation can attract the electron cloud of adjacent anion effectively. But in the case of S and P block element, their effectively they can effectively shield. They can effectively shield the anion basically. So polarization power of cation, it is ability of cation to polarize electron cloud of anion, and polarization power of cation is directly proportional to charge divided by size of cation. So let's move further. It is polarizability of anion. Polarizability of anion. In the case of polarizability of anion, it is tendency of any anion to get polarized by cation. It is tendency of anion to get polarized by cation. And polarizability of anion is directly proportional to its charge multiplied by size. Bigger will be anion, it has more loosely bounded electron and it can easily polarized. Similarly, as negative charge increases, it has more loosely bounded electron and again it can easily polarized. So polarizability of anion is directly proportional to its charge multiplied by size, let's say. So, according to Fazan's rule, rules as either polarization power of cation or polarizability of anion increases. According to Fazan's rule, as either polarization power of cation and polarizability of anion increases, molecule acquired more covalent character. Molecule acquired more covalent character. If it has more covalent character, or you can say it has less ionic character, it acquired more covalent character, and thus its melting point, boiling point, so its melting point / boiling point and solubility in polar solvent. And its solubility in polar solvent decreases. So obviously all these are the property of ionic compound: high melting point, high boiling point, solubility in polar solvent. But as this ionic compound acquires certain covalent character, its melting point will decrease, its boiling point will decrease, its solubility in polar solvent will decrease. Keep writing your notes. So melting point, boiling point, and solubility of polar solvent decreases. So further, let's say you can just try to revise few terms related to as per question is concerned. Arrange following into decreasing order of. Arrange following into decreasing order of their percentage ionic character. Or the question may be, let's say you have to arrange following into increasing order of their percentage covalent character. So first example is, this may be LiCl, this may be NaCl, it is KCl, and let's say it is RbCl. So here we have common anion, chloride ion. So they all have same polarizability as per chlorine is concerned. But lithium plus, as its size is smallest, so lithium plus has maximum polarization power. Lithium plus has more polarization power than Na plus. Na plus has more polarization power than K plus. And K plus has more polarization power than, let's say, rubidium plus. So as per percentage ionic character is concerned, RbCl will be more ionic. RbCl will be more ionic than KCl. KCl will be more ionic than NaCl. And NaCl will be more ionic than LiCl. As you know, rubidium plus consists least polarization power, and Li plus consists maximum polarization power. Similarly, if it is, let's say, NaF, this may be, let's say, NaCl, it is NaBr, and let's say it is NaI. So again here, cation is found to be same, but anion may be fluoride ion, chloride ion, bromide ion, and iodide ion. So as per polarizability is concerned, fluoride ion consists least polarizability, and iodide ion consists, maximum polarizability. So it is NaF should be most ionic than it is NaCl. NaCl will be more ionic than NaBr, and it should be more ionic than, let's say, NaI. Similarly, if we have another compound as it is NaF, or simply you can say it is NaCl, it is MgCl2, and it is AlCl3. So, as per percentage ionic character is concerned, again it is chloride ion. So chloride ion means they consist same polarizability. So only the change part is correspondingly cation and their polarization power. Al3 plus has smallest size and maximum charge. So Al3 plus should have maximum polarization power also. Maximum polarization power means maximum covalent character. So as per its decreasing ionic character is concerned, it is NaCl more than MgCl2 more than AlCl3. Similarly, if we have, let's say, NaF, it is Na2O, it is Na3N. In this case, NaF will be most ionic than Na2O, and Na2O will be more ionic than Na3N. Since in this case cation is found to be same, so you can say polarization power of cation will be same. Only the difference is polarizability of anion. Here N3 minus consists maximum negative charge, and nitride ion also consists maximum size. On opposite thing, if you see fluoride ion is least size, least charge, so it have less polarizability, it has least polarizability. Okay, now move further. As per covalent bond is concerned, according to it's according to Lewis octet theory, B part, let's say covalent bond. So this bond is formed due to sharing of electron. This bond is formed due to sharing of electron. Due to sharing of electron. For example, somewhere you have seen already in the case of F2, fluorine, these may be 7 electron in the valence shell of fluorine, and another fluorine also consists 7 electron in their valence shell. So as per sharing of electron is concerned, this may be fluorine and fluorine gets shared, and let's say these 2 electron get shared between these 2 fluorine. Now due to sharing of electron, both fluorine acquired their octet. Now in the valence shell or outermost shell of fluorine, they consist 8 electron each. So this bond is formed due to sharing of electron, let's say F2. So for example, I can take another thing as, let's say, NH3. Nitrogen valence shell consists 3 electron unpaired and 1 electron may be paired in their valence shell. They consist 5 electrons. Same, they may each connected with hydrogen. It is another hydrogen atom here and another hydrogen atom here. So in the case of valence shell of nitrogen, they consist 8 electron and 2 more electron with this hydrogen and 2 electron get combined with this hydrogen, let's say. So this is the structure of NH3. and there's another structure as F2 fluorine. So this bond is formed due to sharing of electron. So we have some concept including, let's say, bond pair and lone pair of electron here. So bond pair, let's say VP means it is pair of electron which get shared between two bonded atom. And another definition you can say it is lone pair, let's say LP. So it is pair of electron in valence shell. It is pair of electron in valence shell which does not participate in bonding. Which does not participate in bonding. So bond pair as well as lone pair of electron. So lone pair means it is the pair of electron in valence shell which does not participate in bonding. For example, if you see the structure of F2 and NS3, in the structure of fluorine, this is the pair of electron which does not participate in bonding, although it is the part of valence shell. Similarly, this is the pair of electron which does not participate in bonding, and it is the part of valence shell of electron. So this is also known as, let's say, lone pair. Lone pair of electron. Similarly, here, if you concentrate on nitrogen, so these are the two electron which is the part of valence shell of nitrogen, but it does not participate in bonding. So it is also lone pair of electron. So the meaning of lone pair of electron is it is the electron pair in valence shell which does not participate in bonding. And obviously bond pair of electron means it is the pair of electron which get shared between two bonded atoms. Here, let's say I can take another example. This may be, suppose, example as H2O. So as per oxygen is concerned, it can form, let's say, two bond. Its valence electron is found to be 6, and to complete its octet, it required to form two bonds. So now its octet is completed. As per its valence shell is concerned, oxygen consists 6 electrons. Out of 6 electron, 2 electron participate in bonding. So here 2 electron get shared between oxygen and hydrogen. So as per this pair of electron and this pair of electron is concerned, this pair of electron is bond pair of electron, and it is lone pair of electrons. So in the case of H2O, we have one bond pair and one lone pair of electron. Now apart from bond pair and lone pair of electron, apart from sharing of electron, it is another bond which is also known as coordinate covalent bond. So it is the third bond. coordinate covalent bond. So you can say this bond is something very similar to that of covalent bond. So this bond is formed due to a sharing of electron. This bond is formed due to sharing of electron, but both electrons are contributed by same element. This bond is formed due to sharing of electron, and here you can say both electrons are contributed by same element only. For example, if it is A has one electron, B also has one electron, the two can form due to sharing of electron. So the electron of A gets shared and simultaneously electron of B gets shared. So A has one electron, B has one electron, and now between A and B, we have two electrons get shared between them. This bond is going to be the example of normal covalent bond and represented by A bond with B. So it is the example of normal covalent bond. Similarly, if A has both the electron and B has nothing, so firstly it can transfer one electron to B, and A acquired, let's say, positive charge and one electron here. Now B acquired negative charge and now one electron appeared on B. Now they have two electron, one each with on A plus and B minus, and due to sharing of electron, here you can say due to sharing of electron, it is something very similar to formation of covalent bond. This bond should be represented as A plus normal bond and B minus, or this bond may be represented as, let's say, A arrow towards B. So one is covalent bond and another may be, let's say, coordinate bond. So this bond is the example of, let's say, coordinate bond. So coordinate covalent bond is, this bond is formed due to sharing of electron, but both electrons are contributed by same element only. For example, in this case, it is A bonded with B, normal bond, and this A bonded with B, it is coordinate bond here. So this is the difference between covalent bond and coordinate bond. So here, if you see example, ammonium chloride consists all three types of bonds. Ammonium chloride consists all three types of bonds, as here, if you see ammonium ion, it is nitrogen, it is connected with hydrogen, hydrogen, and hydrogen, and hydrogen, and positive charge on the nitrogen, and it is chloride ion. So it consists confirmly three covalent bond, one coordinate bond, and ionic bond between, ammonium ion and chloride ion. So ammonium chloride may consist all three types of bond. It consists cation and anion, so confirmed it is ionic bond. And in ammonium ion, we have three covalent, one coordinate bond. Now, before we move to valence bond theory, we have to see the limitation of octet theory also. So, one of the limitation of octet theory Now, if you see the basis of bond formation in octet theory is to complete their octet, to complete their duplet. But we have many compound exist in the nature. They form bond, but they do not complete their octet or duplet. So you can say limitation of octet theory may be one of the common limitation is existence of super octet and sub-octet compounds. Existence of super octet and sub-octet compounds. The meaning of superoctet and suboctet is if we have compound as, let's say, BeCl2, if we have compound as, let's say, BeCl2, and let's say we have compound as BF3, as per BeCl2 is concerned. So let's say if you see the existence of suboctet and superoctet compounds, in the case of BeCl3, beryllium outermost shell consists only 2 electrons, and as per beryllium outermost shell concern, it consists only 2 electrons in their valence shell, and 2 more get shared with the help of, let's say, chlorine. So even after sharing of electron in the case of beryllium, in outermost shell of beryllium, it consists only 4 electrons. Same in the case of, let's say, BF3. In the case of BF3 also, here, let's say we have 3 electrons present in valence shell of boron and 3 get shared with fluorine. So overall, as total number of electrons are concerned, here total number of electrons we have, let's say, 6 electrons here in the case of BF3. So we have existence of superoctet and suboctet compounds, including, let's say, BeCl3 and BF3. Simultaneously, we have another set of compound. Let's say one is PCl5 and it may be, let's say, SF6. In the case of PCl5, phosphorus pentachloride, phosphorus already consists 5 electrons in their valence shell. Phosphorus already consists 5 electrons in their valence shell, and sulfur already consists 6 electrons in their valence shell. So let's say it is SF6. In the case of PCl5, in the case of PCl5, phosphorus outermost shell consists 10 electrons. Here, it consists 10 electrons in the valence shell even after bonding. And in the case of, let's say, sulfur, after bonding in the valence shell of sulfur, it consists, let's say, 12 electrons. So if total number of electron is less than 8 in valence shell after bonding, these compounds are known as suboctet compound. suboctet or electron deficient compound. Electron deficient compound, and if total number of electron is more than 8, these type of compounds are known as superoctet or expanded octet compound. They are superoctet or expanded octet compounds. I hope you have noted down the definition of suboctet compound and superoctet compound, and simultaneously expanded octet and electron deficient compound. So this is one of the common limitation of octet theory. Here bond can be formed even in absence of completion of octet. Further, we need another theory known as valence bond. Valence bond theory, VBT. And as per VBT is concerned, here any covalent bond is formed due to overlapping of half filled. Any covalent bond is formed due to overlapping of half filled valence orbital. So any bond is formed due to overlapping of half filled valence. So any covalent bond is formed due to overlapping of half filled valence orbital. For example, I hope you learn about type of orbital in atomic structure chapter, in which we have s orbital, p orbital, d and f orbitals. So any covalent bond is formed due to overlapping of half filled valence orbital. Here, for example, in the formation of F2. In the formation of F2, fluorine. So as per fluorine electronic configuration is concerned, its ground state electronic configuration is 1s2, 2s2 and 2p5, which may also represented by this dibbas, this boxes 1s2 and 2s2, and it is 2p5. Here we have 2 electron in first orbital, another 2 electron, these 2 electron, and we have 1 electron here. Suppose this may be, let's say, as 1s2. This electronic configuration may be, let's say, 2s2 and it is 2p5. So as per this orbital is concerned, it is half filled valence orbital in the case of fluorine. Now out of px, py and pz, this orbital may be, let's say, suppose it is the pz orbital. Suppose it may be px and py also, but suppose if it is 2pz orbital. The meaning of 2pz orbital is, suppose if we have z-axis and let's say if we have fluorine, so this may be one of the 2p orbital here, 2p orbital of fluorine, and same as another 2p orbital of fluorine may be, let's say this is another bond, another overlapping and fluorine forming bond here. So this may be, let's say, overlapping between fluorine and fluorine, and confirmly here you can say this overlapping will be 2p overlapping and the formation of, let's say, F2. Formation of F2 as a fluorine here. Now, as per extent of overlapping is concerned, extent of overlapping is inversely proportional to size of orbitals. If orbitals are relatively bigger in size, their extent of overlapping will be poor. And here, let's say it can form fluorine bond, 2p overlapping. Another bond maybe, let's say, 3p overlapping in the case of chlorine. So if you see, similarly, if we have chlorine bond, it may be, let's say, bromine and bromine bond, and this may be iodine and iodine bond. In this case, this overlapping is going to be 3p overlapping. It is going to be 4p overlapping, and it is going to be, let's say, 5p overlapping. Fluorine consists, 2p overlapping. Now, depending on the orientation of this overlapping, further covalent bond can be divided into two categories. So, depending on orientation of overlapping, depending on the orientation of overlapping, covalent bonds can be divided into two categories. A is sigma bond, or this may be written as sigma bond. So this bond is formed due to this bond is formed due to axial overlapping. As the sigma bond is concerned, the bond is formed due to axial overlapping. And B is, let's say, pi bond. So here this bond is formed due to sideways overlapping. So one is sigma bond. So bond is formed due to axial overlapping. Pi bond, the bond is formed due to sideways overlapping. So depending on the orientation of overlapping, covalent bond can be divided into two categories, sigma bond and pi bond. For example, if we have O2, formation of O2, oxygen electronic configuration may be 1s2, 2s2, 2px2, 2py1, 2pz1. So it has, let's say, two half-filled orbital, two half-filled p orbital here. Now suppose again here we have this as y-axis or z-axis. This may be suppose z-axis and this may be, let's say, x-axis here. This may be one of the oxygen atom and it is another oxygen atom here, and this is one of the 2p orbital. This may be another 2p orbital of another oxygen atom, 2py basically. So obviously it is 2py. We have overlapping of 2py and 2py, and it is clearly seen from this diagram also. It is axial overlapping, but simultaneously, as per 2py orbital is concerned, it is also half filled. 2py orbital is also half filled, and here we have sideways overlapping in 2py and 2py orbital. So this bond is formed due to sideways overlapping, and it is pi bond. Pi bond and due to sideways overlapping. This bond is nothing but, let's say, sigma bond. And this bond is formed due to axial overlapping. So whenever we have multiple bond, there has to be one bond as a sigma, one bond has to be pi. But axial bond is formed due to, sigma bond is formed due to axial overlapping, and pi bond is formed due to sideways overlapping. Now, this is the properties of sigma and pi bond. Properties of sigma and pi bond. First is between two bonded atom, first bond is always sigma. First bond is always sigma, and in the case of multiple bonds, remaining bonds are pi bonds. So between two bonded atom, first bond is always sigma bond, and in the case of multiple bonds, remaining bonds are pi bond. For example, if we have carbon-carbon sigma bond, if we have carbon-carbon double bond, and if we have carbon-carbon triple bond here, this bond is only, let's say, 1 sigma, it is 1 sigma, 1 pi bond, it is 1 sigma bond, and 2 pi bond. Another property between, of sigma and pi bond, between two bonded atoms, between two bonded atoms, sigma bond is always stronger than pi bond. So between two bonded atoms, sigma bond is always stronger than pi bond. And one more point. S orbital always form sigma bond. S orbital always form sigma bond. वही P and D orbitals can form both sigma as well as pi bonds. So S orbital always forms sigma bond. P and D orbitals can form sigma as well as pi bonds. I hope as per today's lecture is concerned, till now in chemical bonding, we have just seen the definition of sigma bond, definition of pi bond. We have seen the meaning of, let's say, extent of overlapping, the meaning of ionic or electrovalent bond, Fazan's rule, and from Fazan's rule we can predict the percentage covalent or percentage ionic character in a given ionic bond. And then apart from ionic bond, it is more related with, let's say, type of bonds, including ionic bond, covalent bond, and coordinate bond. So the difference between covalent and coordinate bond is both are sharing of electron. In covalent bond, one electron each is shared by both bonded atoms. But in the case of coordinate bond, both electrons are contributed by same atoms only. So in the next lecture, we'll continue with valence bond theory. We'll see how we count the number of sigma and pi bond in lone pair of electron. And depending on the sigma and pi bond, in the next class, we'll discuss geometry related to number of bond pair and lone pair, including VSEPR theory and hybridization state. So keep reading from your textbook, you're from state board or, depending on central board, anything, So just read the same chapter from your class 11 textbook, and we'll continue the same in the next lecture also.